All righty.
We're back.
Good morning. Good morning. Good afternoon. Good evening.
Yep. Hello,
I think
all.
we got a huge crowd from around the world online here, which is awesome.
I love that. Looking sharp, Pete.
Thank you. Yeah, I got my hoodie on. There you go.
The official host uniform.
You want to gear up. Tariff-free hoodie. So
Mm-hmm.
while supplies last. Supports our scholarship fund. So actually, if you want the hoodie, I don't know if I have a little banner to show it, but yeah, there you go. Go to our Hoobie site, hoo.be, AJI. You can get a hoodie. It's cool. And it supports our scholarship fund. But I'm getting ahead of myself. I want to just say welcome, Davis. Welcome, everyone, to AJI Talks. And we're here to talk about audio AI and audio ML, which is going to be pretty hot. It's kind of a hot topic these days.
Always evolving. I think one of the folks who've been in the digital signal processing space for a long time will be talking about it. So what's new, of course, as well, AI and adding deep nets to the processing pipeline, getting better accuracy, better feature extraction. So no, we're in store for a cool talk.
Should be good. So a couple of public service announcements, a couple of PSAs. One is that we published, we're going to have a 2-day live stream. It's our third live stream around generative AI and the edge, or generative edge AI, I guess would be the right way to say it, on May 27th and 28th. So we have a call for papers out for that. That's a 2-day live stream, worldwide presentations, academic, industrial. If you have a good idea and want to present kind of a 30-minute, 25-minute pitch on our live streams, go to our website, submit your call for papers, and you too could be famous person. But yeah, we really appreciate all submissions on that. So that's May 27th, 28th. Also, registration's free and it's open, so you could reserve your spot right now. So that's the next big hot thing. And then we have our registration for Milan conference, July 2nd through the 4th is open. And so you can register there. That's going to be a blowout in Italy.
Still got to make it out there. I mean, the Jenny at the Edge, the virtual one, that's a fantastic event that Tinyml and myself have done going back almost actually just about it's been about just a year now since we did the first one, and yeah, I don't know what other landscape is changing faster than Gen AI. Plus, at the Edge, it's
crazy.
It's really sweet to get together, and I think the dialogue, like as usual, that's my favorite part of these kinds of interactions is when someone puts some data out there and it comes contested or interested or
it's a live stream, so we got questions, and we had about 900 people in the last one, so this one's going to be hopefully top that. But yeah. Hot topic. We're also going to be, we have a bunch of partners at Innovex and Computex coming up in May. So if anyone's
that's Taiwan, right? Yeah, Innovex sub. Taipei,
that going on, which is pretty cool. So yeah, always stuff going on. Go to our website, sign up for a newsletter, subscribe, blah blah blah, click links, things like that.
So is Innovex co-located at Computex? Is it?
It is. It's part of Computex. It's more for like the startup thing.
Okay, cool.
We have a lot of startups now in the foundation that are doing lots of cool things, and so we'll have a pavilion of startups.
Awesome. Yeah, I'm always seeing new logos in that intro video. Always one or
new
two
logos. It's hard to keep up. Rosina is in the background here. She's not visible, but she's
the invisible hand of the foundation.
The invisible hand, exactly. Cool. Why don't we bring on Daniel from SIVA, and he's our guest of honor and the audio ML expert. So let's see if we can get him on. There he is.
Hey, Daniel.
Hi, everyone. Hi, Pete. Hi, David.
Hey, good to see you.
Hi.
Thanks for joining us.
And, glad to be here with you.
Let's put you in the proper, you get the guest of honor spot here. So you get the big square, and we'll get the small squares. But yeah, so thanks for joining us. And you're from SIVA. So what do you do at SIVA other than audio AI? All right. So what's your role at SIVA?
Thanks first for letting me be here and this stage in the talk. At SIVA, first of all, I am a PhD in the computer science, specifically specializing in the deep learning, how not. And at SIVA, I'm working at SIVA, have been working at SIVA for the past 6 years, specifically specializing on audio operations for Tinyml domain, which is why we are here. Things like wake word detection, keyword spotting, speech recognition, automatic speech, etc. And today we're going to two of these applications.
Cool. Your audio is a little choppy, and your video is kind of so it's a little rough. I'm not sure if there's a resolution to that, but just to let you know, it's cool.
Do you hear me?
Yes,
it's better when you. It's better all of a sudden, yeah. So I mean, Tinyml is not a new technology to Siva, right? You talked about your PhD and how you've gotten involved. How long has Siva been working with Tinyml? I don't know if you caught the question.
So, but I have a. I don't hear you. Good enough.
All right. This is the live
stream.
Wait a second.
Well, maybe we try to stop talking to you and let you talk through your slides. I think if you reduce the video, it might help us with the audio lag. But it's up to you. I think the main thing today is we want to make sure the audience gets your slides.
Yeah, I have a lot of audio lag. Wait a second.
Right. Why don't we shift?
To switch to another.
Yeah, we'll shift over to that mode.
Yeah.
So you just need to share your slides on the screen thing, and then we'll move into that mode, and then we'll
focus the bandwidth on the presentation.
Yes, we can do that. And so so
I like the logo. I like the trees
cool logo.
That's
good. It's good.
All right, Daniel.
We're waiting for him to share his slides. So he might be having some connectivity issues.
I think you might be frozen. Yeah,
it happens. I had that yesterday. Actually,
yes,
I was talking.
Connectivity.
Yes, you do.
I had you got some serious issues. I had to switch to my,
my
5G phone. Doesn't seem better, but I had to switch to my phone yesterday because for some reason my Xfinity internet was just crapping out on me. So, and I was doing like a recording with someone, and I had to just switch. Actually, it was with your boss. You're with Ollie.
Oh, no kidding. Okay.
Yeah, and it's like all of a sudden it was just like blap, and then I had to just switch to my hotspot on my phone. And
when in doubt, sell data.
That was tough. So we
powered through. Do you hear me better?
Yes, we can hear you now.
I want to say yes. Yeah.
So if you want to share your slides, and then if you want to do camera off, we're cool with that.
We'll manage that.
We can show your camera at the end, but I think maybe the camera is eating up some bandwidth. So yeah, put your slides up there. We'll share them, and then jump into audio AI. Audio is kind of becoming a hot thing. I mean, we have a number of folks in the foundation now. We have Siva, Sentient, who bought the Knowles microphone folks, and a number of other folks doing cool stuff with audio AI, Green Waves, if you remember them. But like you can use audio AI not only for just like higher quality kind of sound, but also doing detection. So seeing audio applications, and hopefully Daniel will talk about that. So using audio as detection. So there's the classic kind of glass breaking, gunshot detection, but also you can listen in like, environmental monitoring. You can be listening for wildlife. You can be distinguishing, bird calls, and how many birds, even insect sounds you can do. So we're starting to see audio used more and more as a kind of a substitute for a camera. So instead of visual detection, you're doing.
Do you see the screen?
There you go. Nice. Awesome. All right, we're gonna back out, but once you get started, Daniel, and then we'll monitor the chat for questions. Everyone, throw your questions in there, and we will gently interrupt Daniel somewhere along the way and to get his questions answered. But yeah, you have the floor, sir.
Take it away.
Okay, so Pete, now you can hear me all? Everything?
Yes, sir.
Okay.
Go for it.
Yes. Good to know. Wow, it was very, very hard, bumpy ride.
You're good.
Okay.
You're good.
So Hello, everyone. Thank you first all for you to join us. Today we will explore two audio applications within the Tinyml domain. We will cover the entire process from development through to deployment. Specifically, we will discuss about environmental noise cancellation and also text-to-model applications. Okay, so we at Silva, we have identified three key stages every neural network model goes through. The first stage is the development stage, where we design the architecture, we need to gather in data and training the model. Once the model meets our criteria, we can move to the productization stage, where we optimize the model efficiency in size and complexity using methods like quantization, pruning, compression, knowledge distillation, etc. Finally, for deployment on Siva's MCUs family, we convert the model from PyTorch to LightRT for microcontrollers, or if needed alternatively, we directly implement the model in C code. Okay, so we will start with the environmental noise cancellation, in short, ENC application. So I think that as everyone knows, human-to-human communication is largely occurs through devices such as smartphones, video conferencing, and other digital platforms. To maintain these clear conversations, it is essential to reduce the background noise captured from the environment. For example, if you are at home, you can have a lot of baby cry, dog barks, other ambient noise, or if you are outside, you can have car horning, plane, etc. A lot of noises. Additionally, as human-to-machine interaction become more prevalent, automatic speech recognition, known as ASR systems, require high-quality audio signals to function reliably. Therefore, ENC applications play a crucial role in facilitating clear and effective communication, whether human-to-human or human-to-machine applications. Okay, so specifically in Siva, at Siva, we chose DFilterNet 3 to be our architecture for the ENC solution due to its excellent combination of features, which are, first of all, its single channel support, which is ideal for any microphone enabled device. Secondly, it uses full band processing, allowing us to support any sample rate from narrow band up to the full band systems. Also very important is the causal design of the model, achieving low latency of only about 40 milliseconds, which is good enough for all far-end applications. And finally, and the most important one, is that it also an optimal balance between the quality and efficiency. Okay, so how the architecture itself looks like. So the DFilterNet architecture consists of three parts: the encoder, ERB decoder, and the DFilterNet decoder. And the encoder accepts two inputs. First is the complex features, the complex spectrogram up to 5 kilohertz generated by a short-time Fourier transform, in short is the STFT. And the second input is the equivalent rectangular bandwidth, which is the ERB features, approximating the human auditory filters, modeling how humans perceive the sound. Next, we have the ERB decoder, which predicts the ERB gains, acts as a mask between for frequencies between bins around 5 kilohertz, above 5 kilohertz. And the last one is the deep filter decoder, which estimates the deep filter coefficients to reconstructing the periodic structure of the speech signals up to the 5 kilohertz. And as you can see here now, as you can see the entire architecture, you can see that the model employs a convolutional neural network and the gated recurrent units layers to capture both local and temporal dependencies. And it also uses group linear layers to significantly reduce the model size and its complexity. Okay. After extensive evaluation inside SIVA, we identified 3 scenarios where the deep filter net 3, the original one, wasn't sufficiently stable for our needs. The first one was when the signal contained non-English language. The second one was where the signal has a low speech levels, around minus 50 dBSL, below that. And the third one was in rapid transitions between different speech intensities. To address these weaknesses, we made several modifications, as can see in the table below. The first change was at the encoder is a feature combination method from addition of 2 features to concatenation of them. The second one was to increase the convolutional feature maps from 64 to 96. The third change, modification, was to reduce the GRU units, specifically in the ERB decoder, from 256 to 128, because we see that it doesn't need more than that. Fourth, we apply the ERB gains, as we recall the mask for the frequency bins, to all the frequency bins and not just the one above the 5 kilohertz. And lastly, we also trained our model with multilingual data and not as originally the model trained only on English. Okay, once we have been satisfied with the model's performance, our model, we applied 2 optimization techniques to further enhance the suitability for microcontrollers, because as we mentioned at the beginning, we want to deploy it on the MCUs at the end. So we first apply the quantization-aware training technique and also the singular value decomposition compression, which we both explain in the next slides. So in quantization-aware training, we apply the fake int 8 quantization to the weights during the forward pass, while we maintain the full precision during the backpropagation. This method allows the model to account for the quantization effects during the training, significantly enhancing the robustness in the inference. Quantizing weights to int 8 reduce the memory usage by 4 times, which is a substantial reduction in memory. On the right, you can see an example of this flow, what we explain on a single fully connected layer. But again, when we have a big model, it will be on the entire model. This is just an example to illustrate how it works. Okay. In addition to the quantization-aware training, the SVD involves mathematically decomposing every 2D weight matrix M into 3 matrices, U, S, and V. We encourage during the training to sparsity in the singular value matrix S by integrating the regularization terms to the loss. After training, we eliminating the 0 value elements from the S matrix, allowing corresponding rows and columns from the U and V, respectively, to also be removed, which you can see in the left side. This results in a compressed representation of the original matrix M, achieving an optimal balance between the compression and the performance, which can be easily controlled by the regularization coefficients that we can decide on. Okay, following the quantization-aware training and the SVD compression, we obtain an efficient, high-performance model. However, Our goal is to run this model on an MCUs. Our deployment process involves three main steps. The first one is we need to developing a streaming version of the model in TensorFlow, from PyTorch to TensorFlow, which addressing challenges such as cyclic buffer for the temporal convolutional parts, also converting the PyTorch weights to the TensorFlow. If some of you already try it, you know that, for example, in the fully connected, you need to transpose the weight before you move them from PyTorch to TensorFlow. Also, we need to find solution for unsupported layers. Again, I can give an example from the DFilterNet. You have the depth-wise transpose convolution that in PyTorch it exists, but it doesn't supported in the TensorFlow. So we need to recreate a new layer in PyTorch to have the same thing in the TensorFlow. Next, after we have a model in TensorFlow that it is actually working, we need to convert this TensorFlow model into a quantized TensorFlow Lite version of the model, which also handle additional challenges such as unsupported operators, again, because it's in a quantized version, and also creating a calibration data. And each calibration data can give you a different kind of model because it's for the post-processing of the quantization. And third, lastly, we need to ensure that all the operators are compatible with C-wise MCUs, which involve implementing and optimizing unsupported operators specifically for our hardware, for the light RT for microcontrollers. Okay, now for the results. Regarding the performance, we compare our ENC solution with the open source alternatives. As you can see, the x-axis represents the model's footprint in megabytes, while the y-axis indicates the mean opinion score, in short is MOS, which measures the audio quality. The higher the score, the better. The orange rectangular in the upper left corner represents the optimal trade-off between the two metrics. In our model is 8 times smaller than the original DFilterNet, while maintaining performance, making it highly suitable for memory and power-constrained devices. Here, you can see an example demonstrates the performance difference using a customer-provided noisy input signal. Initially, the signal contains background noise. This is the first half of the signal that you are seeing. This is the spectrogram, followed by a speech in Chinese. And again, if you remember, the original DFilterNet didn't train on the other than English language. The original DFilterNet, as you can see, effectively removed the noise, but also overly attenuated the speech signal, which is not what we are designed for. On the other hand, our version successfully eliminated the background noise while preserving the speech, which is the desirable outcome. Okay, so in summary, we took the DFilterNet 3 architecture, identified and addressed its limitation, and significantly improve its robustness while being 8 times smaller. To achieve this, we combined the quantization aware training and the SVD compression technique. And finally, we demonstrate the comprehensive process from initial model development to successful deployment on MCUs. And now let's move on to our second application, text-to-model. Okay, so I believe that all of you have noticed that devices around us are becoming increasingly smarter, often incorporating voice user interfaces for easier and more intuitive operation. For instance, you can imagine how you can talk to your TV without looking for your remote because you don't know where you put it last night. Or, for example, you want to operate your microwave but your hands are busy or dirty. So on highly resource-constrained MCUs, typical voice user interfaces include a wake word detection model to allow the device to know that you are talking to it, and alongside another model designed to recognize a specific set of commands to operate this device. So we have two things here. We have the wake word detection and the keyword spotting model. So from the manufacturer point of view, which is ours, developing a keyword spotting system involves 5 key steps. First, they need to choose a wake word and a set of voice commands, which is hard for itself. After that, they need to acquire the necessary data, a process that can take weeks or even months. And the third step is processing the raw data that we acquired and make it suitable for the training, because sometimes the raw data, it's not exactly what you're looking for. Some of the people that recorded your keywords didn't say it correctly, etc. And after that, we start the training phase, which itself, it's a tedious work and can take several and up to months, several days or up to months. And finally, after we have a model, we need to test it thoroughly to assess its performance. This traditional approach is expensive and highly time-consuming for companies. And even though this process alone, it sounds long enough and very expensive, it doesn't end there. Changes to product, like you want to rebrand the name of the product or change even a couple of the voice commands, often leads to more data collection and retraining, which multiply the cost of the delays by the number of the changes, which is the N. And this is exactly where our text-to-model and solution comes in, to eliminating these costly, time-intensive steps and significantly accelerating the development cycles. So what is actually our text-to-model? So as its name implies, our solution directly generates keyword spotting models using only text input. Our approach consists of 2 main phases. The first one is the registration, which occurs offline on any standard device, can be on server or on your laptop, etc. And the second one is the inference, running in real time on resource-constrained MCUs. So let's take an example.
Daniel?
If you want your model to recognize the wake words.
Hello?
Yes.
Hey,
yeah,
Daniel.
can we jump in for a sec, because we got a backlog of questions. So before you dive into this,
Okay.
Is that okay?
Yeah, sure.
We had a lot of good questions. Davis, you want to tee something up here? What's your favorite?
Well, I think there's a theme that definitely makes sense, which is this PyTorch to TensorFlow conversion step. So I think I can understand why you'd want to take this flow, but I think it'd be great for the audience, based on a lot of the questions, if you can talk about how you made that possible, why you didn't start with TensorFlow in the first place. Have you tried things like Edge AI Torch or LightRT? So maybe just really focus for a second on why you start with PyTorch and how you're able to bridge that gap from PyTorch to TensorFlow for the first use case, deep filtering.
This is a very good question, and I will start with that PyTorch is much more easier platform to develop a model. It's much more agile to changes. You can do whatever you want. And in TensorFlow, we also tried, by the way, working with TensorFlow, but very early in the process of trying to train a model in TensorFlow, we found that here in Siva that it's too complicated. Things were very hard to ramp up. And in PyTorch, when we tried it at the beginning, we see that everything works very smooth. We want to customize the loss functions. It was very smooth. Everything works, out of the box perfectly. And in TensorFlow, it wasn't the case. And as I mentioned, for example, in the example for one of the problems is that in TensorFlow, there is much less new or supported layers. For example, the one that I give you is the depth-wise convolutional transposed convolutional layer, which in PyTorch you have, and somehow in TensorFlow you don't have it. So this is the reason why we choose to always continue with PyTorch, because at the first try it was perfectly for us.
Makes sense.
And what was the other question about it?
Well, there was a few sub questions, but what about when you go to inference? The framework, the PyTorch framework has a lot of overhead and baggage, right? That doesn't make it maybe as edge friendly as TensorFlow Lite. So there are questions on how did you convert? Did you replace certain operations or layer types themselves? Like, if you can talk about that conversion process. So you kind of justified why you used PyTorch in the first place. Now it's like, how did you make it edge friendly?
Okay, now I understand. So I can continue with the same example. For example, if I have the problem with the depth-wise transpose convolutional layer, so yes, you are correct that we need to do some modification in the PyTorch model to be compatible with the TF Lite converter. Yes, we did it. For example, we need to change the layer from this layer to something called sub-pixel convolutional layer. I believe that some of the audience will know what I'm talking about. And then it works smoothly. But the main reason that and another thing that I want to say here is that yes, we need to also make changes both in both edges. We change things in the PyTorch pipeline. I mean, we change the model to be more compatible with the TF Lite, but we also need to change things under the hood of the TF Lite to be compatible with the PyTorch. So it's a symbiotic between the two, and we need to work hard on both of the sides.
Cool.
But again, we choose to always work on the training side of the models in PyTorch because it was much easier. It's still much easier. I mean, we're still training models in PyTorch. And I think that we are not going any soon to change it to TensorFlow.
Yeah. No, super interesting. I think that was a really helpful answer.
But it's a good question, and again, it's a very hard work and tedious work, but this is how it works for now.
There's a couple other ones. Just there's one that's kind of involved here. You know, custom layers of DFN at 3. You're familiar with this? Which data set did you evaluate the DNS MOS? Blah blah blah. So I don't know if you want to get into that level of detail, but
yes. So the MOS that I showed you is the DNS MOS, but this results is not on the let's call it the academic benchmark. We have our own internal benchmark, which is much harder, as I mentioned, multilingual, very dynamic range of speech intensities, because we saw that the DFilterNet 3, the original one, works on a specific range of speech intensities, and when it becomes too high or too low, it just collapses entirely. So what we present here is much more, let's call it representative to the real world.
Okay, cool.
I answer your question?
I think so. Should we carry on, Davis? I mean, we could do questions all day, but I want.
Yeah, I think you're a popular guy, Daniel. So I think we'll have to get back to the slides, and we'll take in next Baxter questions when it makes sense.
Go for it.
Yep. So back to your presentation.
So I can continue.
Please.
Okay. So what is a text to model? Okay. This one I will say it again shortly. So text to model composed of two separate parts. The first part is the registration, occurs offline on any standard device, and the second one is the inference, which will run on in real time on resource constrained MCUs. Here I start to talk about an example of how it will work. So assume that you will want that your keyword spotting model will have three keywords: Alexa, OK Google, and Hello Siva. So we just simply input these phrases during the offline registration phase, resulting in an immediately deployable model, as you can see here. And also it is worth to mention that each additional keyword increases the model size by only about 1 kilobyte, which is very small. The model generated offline is then deployed on the MCU. And when a user say a phrase like, for example, hello Siva, the corresponding keywords is detection probability should spike significantly, while the others, for here in the example it will be the Alexa and Google, OK Google, the probability should remain very low, as you can see. Okay, so how it looks under the hood. So again, because we need to separate between the offline and online the parts, we will start from the offline models. The first module is the graphene to phone module, which gets a text as an input and predicts the corresponding phonemes string formatted in alphabet representation. The second module is the query to filter, which gets a phonemes string from the graphene to phone and generates a filter to a conv1d layer. As you can see, it goes to the online part. Now for the online section, we have first the CTC-based acoustic model without its phone projection layer, and it follows a 2-1-do convolutional layer. Okay, but how it works? So we train our text to model using contrastive learning to project both the text and the audio domains to the same latent space, just as it is a common approach when you want two domains to be in the same latent space in general. Each sample in our dataset consists of a positive text-audio pair and negative pairs created by leveraging other pairs from the same training batch. In other words, we want that all the positive text-audio embedding pairs will have a high similarity, while the negative pairs will have very low similarity. And you can see an illustration on the right, how it should behave, the contrastive loss, in ideal scenario. Okay, to optimize the model for production, we apply quantization error training and again the SVD compression as previously described with the ENC. But additionally, we implemented the knowledge distillation technique, specifically targeting the acoustic module, as it accounts for 99% of the inference parameters module. So in general, knowledge distillation involves transferring insights from a larger high-performance teacher model to smaller model students model. This is how it calls. In our case, the student model is the compressed acoustic module using the quantization error training and the SVD methods. Instead of training the student directly with CTC loss, like we did with the teacher, we found that aligning the student blocks closely with the corresponding teacher blocks result in much better performance and stable training. And furthermore, we use the teacher's projection module to ensure the student predicts similar output labels distributions. And this additional training loss significantly enhance the model's accuracy with the phone prediction. Okay. After we have the model, so regarding the deployment, again, we follow the same steps previously discussed, but as you may guess, it is not the same. I mean that the obstacles will be, the general obstacles for each one of the steps will be the same, but it will be different in the specific details. But it is more or less the same pipeline. Okay, utilizing the production techniques, we mentioned the computational training, SVD, and the knowledge distillation. We developed 3 model variants ranging from 500K down to 250K parameter, which is very small variants. To assess the performance, we use an open source benchmark measuring the true positive rate and false accept rate metrics, which are common metrics when you are developing a keyword spotting model. Our 500K model achieves equivalent true positive rate compared to proprietary alternatives, but with 3 times fewer false alarms, demonstrating its excellent efficiency and reliability. Okay, so to conclude, we designed the system to instantly create a keyword model using only text input. We utilize the quantization overtraining, SVD compression, and knowledge distillation techniques to enhance the efficiency. And finally, we successfully deployed the model on CEVA's MCUs family. And if you want to see our text-to-model in action, we have a demo in our YouTube channel of CEVA. So I encourage you to visit them. And thank you all for listening. Again, if you have more questions than what we will try to cover here, you can reach out through LinkedIn, email, etc.
Awesome.
That's it. Now I think for the questions.
Yeah, now we got plenty of questions.
Great talk, Daniel. Yeah. Thank you. Pete, I would go back to a question earlier that came from Sunny Katri that if you scroll up a little bit farther to around 11:19 a.m. is the timestamp. I thought this was a good question because it is a very, let's say, pervasive use case nowadays, and there's a lot of Bluetooth headsets that have different variations depending on the price point and quality. Daniel, if you can see the question, can you answer what is the advantage of this technology over traditional noise cancellation nowadays available with most of the headsets? Are you there, Daniel?
I don't see the question, but I heard what you are asking, so it's good enough for me. We start at the beginning of the environmental noise cancellation. It was a classic approach, but we very fast we understand that, again, during extensive evaluations, that if we want a single microphone, and this is very important, a single microphone solution for environmental noise cancellation, all the classical techniques are not are fall short and can't really handle it. They need at least 2 microphones or even array of microphones, which is very expensive for low-end devices. So we found that using deep learning models with only single channel information works not good as classical, but even further, much better compared to classical environmental noise cancellation algorithms with multiple array of microphones. So we have only benefits from moving to this approach. Cool. And we are not the only one. Yes, the entire industry going to this direction.
Yeah, deep learning eats everything. Yeah, that's good. But I mean, that's I think you told the story quite clearly.
For the good, the bad, and the ugly.
Yeah. True. I mean, there's another one, Pete, that I don't think you covered before, from Suman Grai around 11:34. Says, hello, sir. I've written a CRNN code in TensorFlow then try to convert it to TF Lite. And Daniel, they're facing an issue due to LSTM layer. So do you have a solution for when you're trying to convert a code in TensorFlow that has a CNN, or no, two questions down from that one actually.
Oh, sorry.
But similar
right
vein. Yeah, similar. There's a lot of conversion questions. So yeah, Daniel, the question is converting in TensorFlow with LSTM layers. Do you have a solution for that? I've heard this problem before as well. I think he's thinking about it.
Again, I didn't hear the question. I see the question. Hello.
Yep.
No, I didn't hear you well because sorry, because the lag.
Yeah.
So this is the question is here below.
Yep. It should be highlighted on the screen. LSTM layer conversion in TensorFlow.
So first of all, I didn't work with the LSTM layer. We are working with the GRU, but to be honest, it works. It should work the same as GRU because it just fully connected. The in LSTM it will be, I think, again fully connected. So I don't see any problem with that. I don't know why. What I can suggest to him is that he can implement by himself the LSTM. This is what we also back in the days did, and it works good. I mean, it can just break the layer. This is my suggestion.
Okay, so you either rewrite it yourself or use a GRU, use a gated recurrent unit. Similar building block, honestly, at the end of the day. So like you said, it should have similar functionality to use a GRU.
And if this is not work for him, he can just re-implement it by itself. You know, a custom, let's call it a custom LSTM, which will do the same property, but it will break much more healthier instead of the native LSTM. This is what I will do.
Nice.
Cool. There's a couple of questions from Shubham Sharma. We can throw those up there. One was around the Kaldi toolkit. Did you use the Kaldi toolkit?
Did you use it? No, not at all.
Okay. Easy answer.
Easy answer. And then there was a follow-up, the model size, which has device used for testing.
Yep.
What was the model size? What was the model size?
Which edge device
used?
So I don't know if the question is regarding the text to model or the diffilternet, but I can tell about both of them. In the diffilternet, we have at the end model of 1 megabyte, not 1 million parameters, but it's the same after you quantize the to int8. And in the text to model, we have a couple of variants from 500 kilobyte and down to 250 kilobyte parameter.
Okay.
Nice. Very edge friendly, pretty compact.
Yes.
In both cases.
Great. Yeah. What other questions we got here? We can go back a little ways, but Davis, you see anything that's
I mean, there's one that was we can get in the weeds here. There's a question about how from Xiaoming, as you had said, how the cyclic buffer concept is represented in PyTorch and TensorFlow. I wasn't sure the answer to this. Maybe Daniel, you can help us answer this question. How is the cyclic buffer concept represented in PyTorch and TensorFlow?
This is a good question. So very, very easy. First of all, in PyTorch, we didn't need to care about the cyclic buffer because the input, it's the entire input itself. And we don't, in the PyTorch, we don't have a streaming model. The model run on the entire signal at once. But when we moved to the TensorFlow and we wanted the model will eat the sequence frame by frame, which is the streaming mode, and the cyclic buffer is just another layer called cyclic buffer, and he calculates at the beginning what is the size of the cyclic buffer, what is the size of the frame of the features, and then he just save it. For example, I will give you an example. If you need to have a cyclic buffer for a convolutional layer that has a kernel size of three temporal features. So you need to store a size or a matrix of size 3 by the number of features, and each time you have a new frame, you need to remove the last one and concat the new one. This is how it works. I hope it answered.
Did you write that down, Pete? Yeah.
Yeah, I got it.
Thanks. I think that was for those who are just in the technical details, that was hopefully sufficient.
Yeah.
In the meantime, we got a couple of new ones actually. I know we have just about 9 minutes here, so maybe go to Alexander's question. Pete, what do you think?
Sure.
This one's interesting.
Oh, this is a long one.
Yeah. So I'll read.
Algorithms.
Yeah. Okay. So they're looking for production-ready RNNs on with advantages over classic spectrum-based recognition approach. So not exactly the title of your topic, but hey, you're here. People are curious what you think.
Yeah, try to understand the question. Not to say I think that it's not related to the question.
So I guess the question is also, do you guys work with time series data like what's questioned here? Maybe not actually is one of the answers.
No,
actually.
no, we are working on audio data, not temperature sensors. No. So again, yes. To be honest, I don't know the answer for this question.
Okay. Fair enough. I think there's other types of networks we can use, and there's other speakers that we've had in the past talk about time series data that Alexander, you can probably go to that. Next one's actually this is speech because it's in the title. Have you tested models for it's Shubham's question? Have you tested the models for keyword spotting or also ASR? So ASR is automatic speech recognition, and the question is ASR with 1 megabyte. Is this possible?
Okay, so of course that we test our model, our text-to-model keyword spotting against ASR, and it's obvious that our solution is better for the specific needs. Why is that? Because in our model specifically, you can insert keywords which are not in the language. The ASR, which trained for general purpose, doesn't know, for example, the name of this man. I mean that you have a lot. For example, Edge AI talks, but no, this is not a good one. But Siva, for example, Siva, it's not a word in the English vocabulary, in the lexicon.
Sure.
So text-to-model can identify it, but ASR most of the time will fall and didn't catch the keyword. So our solution is better than in general ASR for this specific need, for keyword spotting need. And ASR with 1 megabyte, it is possible. No, it's not possible for a general purpose. For our needs, it was possible because we utilized the ASR only to be encoder for the audio, just to capture the audio, let's call it features.
Yep.
So it's different applications.
Yeah,
we didn't use ASR as ASR.
Right.
Got it. Let's see. There's a question here from Bing Huang. Are there open source RNN for audio classifications?
I believe so. Didn't check it because we have our own, but
right.
But I 99% sure that if you will search enough, you will find something.
We've got a couple.
By the way, audio classification can be a lot of things. It can be scene detection, not only keyword spotting.
Right. Yep. Right.
I don't know what the exactly application
use case. Yeah.
For. The challenge is less about sometimes the models, but what data and what data classes and sources are they trained on, and is that something that's useful to your application? That's often where the mismatch can be, not so much on the model, but the training data.
Right. Here's a TensorFlow Lite. Yeah, there's a TensorFlow Lite question here, if that's interesting. How do you determine which operations are unsupported in TensorFlow Lite and which alternatives can replace them without degrading performance?
This is a very good question. So for those of us that work TF Lite, after you convert the model to TF Lite in a quantized way, you can see that if there is unsupported layers in int 8, you will see that the TensorFlow Lite will dequantize. You will add new, for this specific layer, 2 layers before and after. Before it will be dequantized, and then it will operate the unsupported operator in float 32, and then it will have another layer that he adds, which calls quantize. When you have something like this, you understand that in TensorFlow Lite, this specific layer doesn't support quantization, the int 8 quantization, for example. And then what we did is, again, or we try to implement it in the TF Lite itself, in the code. So we change the actual code of the TF Lite. Or alternatively, if we can, and it was easier, we change the operator itself. For example, we can change the activation GELU to the activation RELU if we can. And we saw that, and we of course need to check ourselves that the model didn't degrade the performance of the model. But if it didn't, we benefit from it. So this is the way we are.
Hey, by the way, there's a couple of questions about follow-ups, and so a couple of things is we were going to. First of all, this is a recorded live stream, so you can always come back to our YouTube channel to watch this again, and you can find us on YouTube, obviously. AGI Foundation. Daniel put in some of his contact information in there. We're also going to post a PDF to our Discord server. So if you go to dsc.gg/AGI, which I put in the comments, you can go there and find all kinds of discussions as well. So a few different ways. The other thing to note is the AGI Foundation has a number of working groups, which is kind of collaboration between companies on specific topics. And audio working group was just started, and Siva is chairing that for us. So if you're working at a company that is interested in audio AI, contact us, and we're always looking for new strategic partners and folks to join working groups. So that could be a good venue for you as well.
Yeah, it could be awesome. Yeah, we would love to others to join to this working group. I think that we will create there really interesting stuff, like the one you seen here.
Excellent. Let's see. Any other? We got another. Well, got about like 30 seconds. Anyone? One last question, or maybe we should just call it.
Okay.
Why don't we just call it? Because we got less than a minute left.
Yeah. Yep.
But Daniel, thank you so much for your time. Appreciate it. We got to look at what you looked like before your camera was shut off. Appreciate that. So, but
yes, yes, of course I will do it. I'm very sorry for the internet issues.
No, it sounds we got all the information. Your slides were great, and it was a really good talk, really interactive.
Cool. Thanks everybody for joining, and we'll see you in some future episodes.
Have a great day.
All right, sounds good.
Thank you.
Thank you.